History tells us a clear story about human sight. We learned to grind glass into lenses during the scientific revolution, unlocking the stars and the microscopic world. But a handful of strange artifacts scattered across centuries whisper a different tale entirely. This video investigates the controversial archaeological evidence of precision optics long before their accepted invention. You will gain a complete understanding of a genuine historical mystery that could reshape our view of ancient innovation. We will examine crystal objects that seem to bend light, ask if master artisans worked with tools they never described, and weigh why most scholars dismiss these finds as mere curiosities. What does it mean if the seeds of discovery were planted far earlier than our textbooks claim, but what exactly qualifies as a precision optical device? It is not just any piece of curved glass or polished crystal. A child can use a drop of water to magnify an ant, and ancient artisans certainly knew that certain transparent stones could blur or enlarge an object held close. The anomaly lies in the specific, repeatable engineering of light. True precision optics require shaping a material to an exact curvature, creating a predictable focal point where light rays converge. This demands a controlled grinding and polishing process, a mastery over the geometry of the lens itself. More than that, it implies an understanding of how to correct for visual flaws, the blurring and color fringing we call optical aberrations, to deliver a clear, undistorted image. The historical triumph we celebrate, the moment a human first saw the rings of Saturn or the bustling life in a drop of pond water, rests on this sophisticated control. We credit that leap to pioneers like Van with his exquisite microscopes in the late 1600s, or Galileo and his revolutionary telescopes just decades before. Their devices were not happy accidents. They were the products of a deliberate optical science, a craft that supposedly did not exist in the deeper past. So when we examine an object from 1,000 years earlier and ask if it is a lens, we are not asking if it makes things look a little bigger. We are asking if it contains the ghost of that same precise intention, a silent blueprint for controlling light etched in stone or crystal long before the official story says it was possible. This official story is a precise and well-documented journey. It begins in the workshops of 13th century Italy, where the first wearable spectacles are believed to have appeared. These were simple convex lenses, ground from quartz or glass, set into frames to aid the aging eyes of scholars. It was a practical invention born from the craft of glassmaking and a growing need to read fine script, a tool that spread slowly across Europe over the next 200 years. The next great leap came with the telescope and the compound microscope around the turn of the 17th century. In the Netherlands, spectacle makers experimenting with lens combinations suddenly found they could bring distant ships into view or peer into the hidden structures of a fly's wing. This was not merely an improvement in vision, it was a radical expansion of reality itself. Galileo famously pointed his telescope skyward in 1609, shattering the ancient celestial spheres with his observations of Jupiter's moons and the moon's cratered surface. Shortly after, pioneers like Robert and Van used microscopes to unveil a bustling, unseen world, publishing detailed drawings of cells and microorganisms. These instruments did not emerge in isolation. They were direct products of the scientific revolution, a period defined by empirical observation, mathematical precision, and a drive to quantify the natural world. The lens became the essential tool of this new philosophy, the physical key that unlocked doors to both the infinitely large and the infinitesimally small. According to every standard textbook, this timeline represents a clean, logical progression from a simple reading aid to the complex instruments that fueled a revolution in human thought. It is a story of cumulative knowledge, where each step clearly builds upon the last within a known cultural and technological context. This established narrative is the solid ground upon which we stand. Any claim of precision optics existing long before this sequence must therefore present evidence so compelling, so inexplicable, that it forces us to question the very foundation of that ground. Yet the ground beneath this tidy history begins to shift, with a single object pulled from the ashes of an ancient empire. In the ruins of Nimrud, a royal Assyrian city in what is now Iraq, archaeologists made a discovery that refuses to fit the timeline. Found within the remains of a palace storeroom, buried for over 2,700 years, was a small piece of polished rock crystal. This is the Nimrud Lens, and it is the most famous and contentious piece of evidence in this entire debate. It is not a dramatic object at first glance, roughly the size and shape of a large, flattened almond. Crafted from natural quartz, it is oval, with one face ground into a gentle convex curve. When held, its surface feels smooth, the product of deliberate and careful polishing. Tests have shown it has a focal length of about 12 centimeters, meaning it can concentrate sunlight to a point, or if used close to the eye, magnify an object slightly. To the modern eye, it looks uncannily like a crude but functional lens. The Assyrian Empire of the 8th century before the Common Era was a powerhouse of administration and warfare, not a society we associate with optical science. They left behind vast libraries of cuneiform tablets on law and astronomy, but no manuals on lens grinding. So what was this object? The archaeologist who unearthed it, Henry, suggested it might have been a decorative inlay, perhaps part of a piece of furniture or a statue. But later researchers, examining its shape and optical properties, proposed more active uses. Could it have been a burning glass, used by a craftsman to focus the sun's rays for fine soldering work on intricate jewelry, a craft the Assyrians excelled at? Or perhaps it was a simple magnifier, an aid for an aging artisan struggling to see the fine details on a seal or a tiny cuneiform character. These practical explanations seem plausible, even elegant, fitting the object into a known context of skilled Assyrian craftsmanship. But they hinge on a profound and unproven assumption that someone, nearly 3 ago, understood the principle well enough to shape the crystal for that purpose intentionally. The Nimrud Lens sits at the very edge of possibility, a tantalizing whisper of an idea that the official history says should not have existed for another 2,000 years. The Nimrud Lens did not remain a dusty museum curiosity for long. In the decades after its discovery, it passed into the hands of optical specialists armed with modern instruments, their goal to settle the debate with cold, hard data. Their findings, however, did not provide a simple answer, instead deepening the mystery. The experts confirmed the basic fact: yes, the polished crystal does bend light. It possesses a measurable focal length. But the critical question was one of intent, and here the data painted a more ambiguous picture. The lens surface, while smooth, is not perfectly symmetrical. Its curvature is irregular, suggesting the grinding may have been inconsistent or perhaps not grinding for optical purposes at all. More tellingly, its focal point is very close to the lens itself, only about 12 centimeters away. For someone to use it as a magnifier, they would have to hold it almost touching the object they wish to see, a deeply impractical position for detailed craftwork. This optical imperfection led many analysts to conclude it was unlikely to have been a dedicated tool for magnification or fine focusing. The alternate theory gained strength, that this was not a lens in the functional sense, but rather a decorative cabochon, a polished gemstone meant to be set into a piece of royal furniture, or perhaps a ceremonial scepter as an ornament. In this light, its slight magnifying power is merely an accidental byproduct of polishing a transparent stone into a pleasing, rounded shape, not evidence of optical engineering. Yet even this sensible conclusion feels incomplete. Why choose clear rock crystal, a difficult material to work, for a simple decoration when easier options existed? And if it was purely ornamental, why the specific oval, lens-like form? The modern analysis leaves us in a frustrating middle ground, where the object's physical properties refuse to fully support either a revolutionary or a mundane explanation. It becomes a test in crystal, where what you see in it depends greatly on what you are looking for. While the Nimrud lens remains an ambiguous outlier, another discovery from a different time and place sharpens the focus considerably. On the Swedish island of Gotland, a major center of Viking trade and craftsmanship, archaeologists uncovered a small, polished object in a grave from the 11th or 12th century. This is the lens, named for the island's main town, and it presents a far more compelling case for intentional design. Unlike the oval, irregular crystal from Nimrud, the lens is a carefully shaped disc of rock crystal. Its form is what optical experts call asymmetric biconvex, meaning both sides are curved outwards, but each with a different radius. This is not the shape of a simple decorative bead. It is a specific geometric form known to reduce optical distortion. When modern researchers analyzed it, they found its craftsmanship was remarkably precise for its era. The lens could concentrate sunlight into a hot, bright point, effectively acting as a burning glass to start a fire or solder metal. More intriguingly, if held at the correct distance from the eye, it could magnify an object several times over with a clarity that the Nimrud lens could not achieve. This level of functionality moves beyond accidental byproduct and into the realm of a crafted tool. The Vikings of Gotland were master navigators, traders, and their network stretching from North America to the Middle East. They possessed the technical skill to shape such a difficult material, and a practical need for such a device is easy to envision. A magnifying lens would be invaluable for a jeweler examining the setting of a gem, or a trader authenticating the fine details on a coin or seal. A burning glass would be a reliable way for it to generate a pinpoint flame without a forge. The existence of the lens forces us to ask a new set of questions. Was this a unique object, the prized possession of a single skilled artisan, or does its presence hint at a broader, unrecorded tradition of optical work in the Viking world? If they could make this, what else might they have seen through it? The artifact stands as a silent challenge, a piece of crystal evidence that some form of practical optics was not just possible, but perhaps actively used, centuries before the official dawn of optical science in Europe. The story of the Nimrud lens is inseparable from the story of the man who found it and the era of discovery in which he worked. Henry was not a scientist in the modern sense. He was a passionate explorer and diplomat, driven by a romantic vision of uncovering lost civilizations. When his team excavated the Northwest Palace at Nimrud in the 1840s, they were essentially treasure hunting, pulling magnificent stone reliefs and ivory carvings from the earth with a sense of awe. In that context, the small piece of polished crystal was a minor find, a curious trinket listed among thousands of artifacts. His own published note on the object was cautious. He suggested it might have been a magnifier or a burning glass, but he presented it as one possibility among others, a puzzle piece without a clear place in the Assyrian world he was reconstructing. This measured ambiguity, however, was quickly lost in translation. The very idea of a lens from the time of the biblical prophets was electrifying. It captured the public imagination far beyond the archaeological circles, becoming a symbol of a lost advanced knowledge. The nuance of its report faded, and the object was steadily promoted from a maybe to a definitive fact in the growing genre of alternative history. This shift reveals a controversy less about the crystal itself and more about how we interpret the past. The initial, excited hypothesis, once repeated and stripped of its original caution, hardened into a seemingly historical truth. It created a feedback loop where the lens was no longer judged solely on its own physical merits, but as proof of a pre-existing narrative about ancient technological marvels. This is where archaeology and popular myth often diverge, one building slowly from fragmented evidence, the other weaving those fragments into a more compelling, and sometimes less accurate, story. The Nimrud lens thus exists in two parallel realities, as a modest, ambiguous artifact in a museum drawer, and as a legendary icon of a forgotten science. Understanding this divide is crucial, because it forces us to separate what was actually found from the centuries of meaning we have layered upon it. The lens suggests a practical craft, but what about a technology demanding not just sight, but foresight? Far from the Viking North, another discovery from the depths of the sea presents an even greater puzzle, one where the question of optics becomes a matter of microscopic necessity. In the early 1900s, sponge divers off the coast of the Greek island have stumbled upon the wreck of a Roman-era cargo ship. Among the statues and pottery, they recovered a corroded, lumpy bronze object about the size of a large book. Initially overlooked, it would later be recognized as the most astonishing scientific artifact from the ancient world, the mechanism. This was not a lens, but a complex, hand-powered astronomical computer. Using a system of over 30 precisely interlocking bronze gears, it could predict the positions of the sun, moon, and planets, forecast eclipses, and even track the cycle of the Olympic Games. Its design reveals a sophisticated understanding of celestial mechanics that we did not believe the ancients possessed. The gears themselves are the key to our optical mystery. They are tiny. Some are just a millimeter thick, with teeth cut with a degree of precision that seems almost impossible to achieve with the naked eye alone. The inscriptions guiding its use are finely engraved, the letters barely a millimeter high. To create such a device, the artisan would have needed to see these details with excruciating clarity. This is where the lens question reemerges, not from an artifact found alongside it, but from the sheer physical demands of its construction. Could the master clockmaker who built this have worked without some form of magnification? The idea is difficult to accept. Fashioning and assembling these minuscule components, ensuring the gears meshed perfectly to model the erratic motions of the heavens, would have been an exercise in extreme precision. A simple magnifying lens, perhaps a crystal like the one would transform this from a nearly superhuman feat into a merely extraordinary one. It would provide the practical visual aid necessary to translate a brilliant mathematical theory into a working bronze machine. No lens was found in the wreck, but its absence is not proof. The mechanism itself is a ghostly imprint, a testament to a level of technical achievement that logically implies the use of tools we have yet to discover. It stands as indirect evidence, whispering that the knowledge to shape light and the knowledge to model the cosmos may have been companions in a forgotten workshop. The mechanism forces us to consider a world where hands could craft what eyes could barely see. This question of vision extends beyond complex machines to the realm of breathtaking beauty. Across the Roman Empire and in the workshops of ancient Egypt, artisans produced objects of such minute and perfect detail that they seem to defy the limits of unaided human sight. Take, for instance, the Lycurgus cup, a stunning Roman glass cage cup from the 4th century. It is a masterpiece of dichroic glass, meaning it changes color depending on how light passes through it. Held in one light, it appears a jade green. When lit from within, it glows a deep, translucent ruby red. This effect was achieved by impregnating the glass with minuscule particles of gold and silver, each one smaller than a grain of sand, meticulously measured and mixed. The cup itself is also a feat of lapidary work, carved from a single thick block of glass into an intricate openwork scene depicting the myth of King Lycurgus. The fine, delicate strands of glass forming the cage around the inner vessel are precisely carved, requiring control that borders on the surgical. How did a Roman glassmaker, without modern chemical analysis or precision tools, consistently produce this nanoscale metallic mixture and then carve it with such confidence? Could they have done it entirely by feel and estimation? The possibility seems remote. A simple magnifying lens would have allowed the artisan to monitor the consistency of the molten glass mixture, to inspect for bubbles or imperfections, and to guide the delicate carving tools with greater assurance. This would not be a telescope pointed at the stars, but a practical workshop aid, a silent partner in the creation of luxury. The same question echoes from countless tiny, engraved gemstones known as intaglios. These were used as seals, pressed into wax to leave a personalized mark. To serve their purpose, the engraving had to be perfectly clear in reverse. Craftsmen worked on stones like amethyst, carnelian, and onyx, often no larger than a fingernail, carving portraits, mythological scenes, and intricate patterns with lines finer than a human hair. The detail is astonishing. On some examples, you can distinguish individual strands of hair on a miniature portrait, or the delicate feathers on a carved eagle's wing. To achieve this, the engraver used a bow-driven drill and abrasive powders. One slip, one groove cut a fraction too deep, and the entire stone, representing days or weeks of labor, would be ruined. Working at this scale without any visual enhancement would be like trying to paint the Mona Lisa on a grain of rice while looking through a fogged window. The strain on the eyes, the sheer probability of error, becomes overwhelming to consider. A simple crystal magnifier, however, would change everything. It would bring the tiny workspace into clear focus, allowing the artisan to see the progress of each cut, to correct curves, and to achieve the crisp, sharp lines that define their craft. This suggests a different kind of optical history, one not written in scholarly texts about the nature of light, but embedded in the silent, practical knowledge of master craftspeople. Their lenses, if they existed, were not philosophical instruments. They were extensions of the hand and eye, tools for making other beautiful things, and their existence may have been so commonplace in high-end workshops that no one thought to write it down. The absence of a magnifying lens in an archaeological record filled with objects that seem to demand its use is a haunting silence. It asks us whether we have been looking for the wrong thing, searching for scientific devices, while the true evidence of ancient optics is staring back at us, engraved in gemstone and glowing in a cup of glass. The artifacts are silent, but what of the written word? Could ancient texts contain overlooked hints of optical knowledge? The search leads us to the great libraries of Rome and Greece, where philosophers and naturalists describe the world in careful detail. One of the most compelling references comes from the Roman statesman Seneca, writing in the 1st century. In his Natural Questions, he describes how letters, when viewed through a glass globe filled with water, appear larger and clearer. This is a precise, almost clinical observation of a refractive effect. Seneca, however, was not describing a tool for seeing. He was using the phenomenon as a philosophical analogy for how the mind can clarify confused ideas. The water-filled globe was a curiosity of nature, a parlor trick to illustrate a point, not an instrument of discovery. His passage demonstrates that the magnifying property of certain shapes was known and observable, but it stops short of revealing any practical application or crafted lens. Similarly, Pliny the Elder, that voracious compiler of Roman knowledge, writes in his Natural History about the use of emerald lenses by the Emperor Nero, who watched gladiatorial games through a concave gem to correct his nearsightedness. This is often cited as early evidence for corrective lenses, yet Pliny's account is frustratingly brief and ambiguous. Was Nero using a carefully ground emerald with a specific optical curve, or was he simply holding a deeply colored, transparent stone to his eye to cut the glare of the sun, its slight curvature and incidental benefit? The text does not say. Classicists and historians of science lean toward the simpler explanation, viewing these references as descriptions of natural phenomena or ornamental objects, not as records of technological invention. The leap from noticing that a water droplet enlarges an ant to deliberately grinding a lens to a specific prescription is a vast one, and there is no clear textual evidence that such a leap was made. Even earlier, the Greek playwright Aristophanes, in his comedy The Clouds from the 5th century before the Common Era, has a character mention a burning glass, a transparent stone used to melt wax and erase a debt tablet. This could refer to a simple magnifying lens used as a tool, but it is a single, passing joke in a satirical play. It proves the concept of focusing sunlight was known, but not how it was achieved. Could it have been a naturally occurring crystal or a piece of shaped glass? The line gives no technical details, leaving us again in the realm of tantalizing possibility rather than confirmed fact. The pattern is consistent across cultures. Chinese texts from the Han Dynasty and later also contain scattered mentions of fire mirrors and seeing aids, but these descriptions are poetic and lack the engineering specifics that would confirm the existence of precision-ground optics. They speak of effects, not of designs. This collective vagueness is, in its own way, significant. If lenses were a standard tool of scholars or craftsmen, would they not be mentioned more directly, their construction and use explained? Their absence from technical manuals and their presence only as metaphors or curiosities suggests that while the principles of light bending were observed, they remained on the periphery of applied science. The texts act like a faint, distorted reflection, showing us something familiar, yet refusing to come into clear focus. They remind us that the past often speaks in riddles, and the hardest evidence to interpret is sometimes the words left behind. This brings us to the one place where the historical record is perfectly clear, a development that everyone agrees marks the true beginning of optical technology as we know it. By the late medieval period, across the scriptoriums and monasteries of Europe, a simple tool became commonplace, the reading stone. This was a hemisphere of glass, flat on one side and convex on the other, often set into a simple frame or handle. A monk or scholar would place the flat side directly onto a manuscript, and the curved glass would magnify the letters beneath it, turning a blur of ink into legible text. These were not spectacles. They were heavy, stationary aids, but they were undeniably lenses crafted for a single, explicit purpose: to correct the failing vision of age. Their invention is a logical, beautiful step in the story, born from the glass-making centers of Venice and Germany and fueled by a rising demand for books and learning. They represent the moment observation turned into application, where the understood property of a curved surface was finally harnessed to solve a widespread human problem. This is the uncontroversial, well-documented precursor to the eyeglasses that would follow in the 13th century. So why does this accepted history matter to our mystery of much earlier optics? Because it establishes a crucial dividing line. The reading stone is a plano-convex lens, a simple shape with one flat and one curved face, designed to sit on an object. The controversial claims we have been exploring, however, point towards something different: the possibility of purpose-ground, handheld magnifiers, or even more complex optical systems. A handheld lens must be shaped differently, often with curves on both sides, to be held at a specific distance from both the eye and the object. It requires a more nuanced understanding of focal length and ergonomics. The reading stone is a magnifying window laid atop a page. The hypothetical ancient lens is a dynamic tool held in the air, a key for unlocking detail at a distance. This distinction is everything. The medieval reading stone fits neatly into a documented technological and social context: the rise of universities, the proliferation of texts, the aging eyes of dedicated scribes. It has a clear lineage and a clear reason for being. The Nimrud, or objects if they were true lenses, have no such context. They float in a historical void, isolated artifacts, without a supporting culture of optical science, without treatises on their manufacture, without a clear, documented need that would explain their invention and refinement. The accepted story of the reading stone, therefore, does not disprove the earlier anomalies. Instead, it highlights their profound strangeness. It shows us what the beginning of a genuine optical tradition looks like: a slow, traceable evolution from a simple aid to ever more complex instruments. The controversial evidence suggests not the slow dawn of an idea, but fleeting sparks of technical insight that appeared, were used perhaps by a few master craftsmen, and then vanished without igniting the broader intellectual fire. One is the start of a continuous path of progress, the other is the echo of a path not taken. But a single, simple reading stone was not the final word. As the Islamic Golden Age flourished in the 9th century, a new figure emerged, one whose story blurs the line between legend and technological history. In the vibrant city of Al lived the polymath Abbas. He was a poet, an inventor, an astronomer, and he is famously credited with constructing a reading stone of his own design. Historical accounts describe him creating a corrective lens from clear quartz or glass, mounting it in a frame to assist with reading. This was not a stationary hemisphere laid on a page, but a more advanced, wearable device, a significant step beyond the basic reading stone. His work did not occur in a vacuum. It was part of a brilliant intellectual movement where the science of light, or optics, was being rigorously studied. The towering figure in this field was Al, known in the West as. His monumental book of optics, written in the early 11th century, systematically dismantled ancient Greek theories of vision. Through experiment and observation, he correctly argued that light rays travel in straight lines from objects into the eye, and he meticulously studied reflection, refraction, and the nature of shadows. His work laid the essential theoretical groundwork for all future optics. He even described the camera, a dark room with a pinhole that projects an inverted image of the outside world, demonstrating a profound understanding of how light behaves. Yet, here lies a critical distinction. Genius was in explaining the principles of light itself. His treatise is a masterpiece of physics and geometry, a foundational text that would later inspire European scientists like Descartes. But it is not a manual for craftsmen. Nowhere in his detailed analyses does he describe the practical art of grinding a piece of glass or crystal to a specific, repeatable curvature. He gave the world the theory of the lens, but not the step-by-step instructions for creating a high-precision one. This separation is vital. It shows that a society could possess a sophisticated scientific understanding of optics, far beyond that of medieval Europe, and still not necessarily translate that knowledge into the widespread production of advanced optical tools. Abbas' reading stone, then, stands as a fascinating pivot point. It suggests the practical application of optical principles was within reach, nurtured by a culture that valued both theory and invention. But does his device represent a lone experiment, a brilliant one-off, or the visible peak of a broader but lost craft tradition? The historical silence on precision lens crafting, even in the midst of this golden age of science, leaves that question hanging in the air, a reminder that theoretical knowledge and workshop technology do not always advance in lockstep. The most audacious claim in this entire debate pushes the idea of ancient optics beyond the workshop and into the stars. Some researchers and alternative historians point to the astonishing astronomical achievements of the ancient Greeks and ask a radical question. Could they have seen more than we think? The argument centers on figures like Aristarchus of Samos, who in the 3rd century before the Common Era proposed a heliocentric model of the solar system, placing the sun, not the earth, at the center. Others, like Hipparchus, calculated the distance to the moon with remarkable accuracy and catalogued hundreds of stars. The precision of these observations, the argument goes, seems to exceed what should be possible with the naked eye alone. How could they have known, for instance, that the planet Mars exhibits a reddish hue, a subtle color distinction difficult to discern without aid? The most provocative suggestion is that these scholars might have used simple, tubeless telescopes, perhaps just a pair of lenses in a wooden frame, to enhance their view of the night sky. This would explain their advanced knowledge not as pure mathematical genius, but as the result of enhanced observation, a technological secret lost to time. It is a compelling narrative, one that connects the dots between the crystal artifacts and the pinnacle of ancient science, suggesting a hidden thread of optical technology running straight through the heart of classical learning. The counterarguments from mainstream historians of science, however, are systematic and overwhelming. They begin with the simplest point, the complete and utter silence of the historical record. The Greeks were prolific writers, passionate about explaining their methods and philosophies. We have detailed texts on geometry, mechanics, and astronomy, If they possessed a device as revolutionary as a telescope, an instrument that literally brought the heavens closer, it is inconceivable that not a single philosopher, poet, or historian would have described it, praised it, or even mocked it. The absence is deafening. Furthermore, the optical theory necessary to understand how to combine lenses to create a functioning telescope simply did not exist in ancient Greece. They understood basic reflection and some properties of refraction, but the complex mathematics of focal points and image formation, the very principles required to deliberately engineer a telescopic system, were developed more than 1,000 years later. Building a telescope by accident is exceedingly unlikely. It requires aligning two specific types of lenses at a precise distance. Without the underlying theory to guide them, such a discovery would be a fluke of cosmic proportions. The achievements of Greek astronomy, while impressive, are also fully explicable with naked-eye observation, relentless dedication, and brilliant deduction. Hipparchus's star catalogue and lunar calculations were the product of generations of meticulous records, using simple instruments like the armillary sphere and the to measure angles with painstaking care. The reddish tint of Mars is indeed visible to the unaided eye on a clear, dark night, especially when the planet is bright and high in the sky. What we see as unexplained precision is often the result of a cultural and intellectual context we have underestimated, a tradition of observing and recording that span lifetimes. To attribute their success to a secret lens is, in the view of most scholars, to diminish their true genius. It replaces the hard-won, documented triumph of human reason and patience with a speculative piece of lost technology. The telescope claim, therefore, stands as the outer boundary of the controversy, a hypothesis that seeks to solve one mystery by invoking another, even greater one. It asks us to believe not just in a lost object, but in a lost chapter of science, deliberately unrecorded by the very people who love to record everything. The weight of the evidence, from textual silence to theoretical gaps, leans decisively against it, anchoring the telescope firmly in its rightful place centuries later. Yet the persistence of the question itself is a testament to the enduring awe we feel for what the ancients accomplished with their eyes, their minds, and the naked sky. The debate over ancient optics finds a surprising parallel centuries later, not in the stars, but on the canvas. A separate but equally provocative theory suggests that some of the Renaissance's most celebrated artists, masters like Caravaggio, may have employed optical devices to achieve their breathtaking realism. This is not about grinding lenses for science, but about bending light for art, a secret tool in the quest for perfect perspective and divine illumination. The camera, that simple dark room with a pinhole described centuries earlier by, is at the heart of this idea. By the 15th and 16th centuries, the principle was well known. A small hole in one wall of a darkened chamber would project an inverted, color-accurate image of the outside world onto the opposite wall. For an artist, this was a magical tracing tool, a way to capture the precise geometry of a scene, the subtle gradients of light and shadow, with almost photographic accuracy. Some art historians and researchers point to specific qualities in certain paintings as potential evidence. The works of, for instance, exhibit a peculiar soft focus in some areas and razor-sharp detail in others, an effect reminiscent of a lens's shallow depth of field. The scale and perspective in his interiors are so mathematically perfect, and the play of light on surfaces so precisely observed, that some argue he must have used a camera, or perhaps even a primitive lens-based projector, to compose his scenes. Similarly, Caravaggio's dramatic lighting, where figures emerge from inky blackness as if caught in a single, powerful beam, has sparked speculation about controlled studio setups that mimicked projected images. The theory proposes that these artists were not cheating, but innovating, using the best available technology to serve their vision, much like a modern photographer uses a camera. Their genius would then lie not in superhuman draftsmanship alone, but in their ability to interpret and enhance these luminous projections, to imbue them with emotion and narrative. This artistic use of optics sits in a fascinating middle ground. It occurs before the official scientific revolution, yet within a period of rapidly advancing practical knowledge. It suggests a world where the line between art and science was beautifully blurred, where understanding light was as crucial to a painter as to a philosopher. The controversy here mirrors the one surrounding ancient lenses. It revolves around intent, evidence, and our willingness to re-examine how masterpieces were made. If true, it does not diminish the artists, but rather connects them to a longer, hidden history of humans using technology to capture reality. A history that may have begun not with a telescope, but with a painter tracing light on a wall. Perhaps the most dramatic example of seeing the modern in the ancient lies not in a polished crystal, but carved in stone on a temple wall. Deep within the crypts of the Hathor Temple in Egypt, a series of enigmatic reliefs have sparked a modern myth that powerfully illustrates the dangers of misreading the past. The images show a large, bulbous object, often described as resembling a giant light bulb or a Crookes tube. Inside this shape, a snake stretches along a line, and a figure stands beside it, as if holding it up or presenting it. To a viewer steeped in 20th century technology, the resemblance to an electric light bulb, complete with a filament and a socket, can be startling. This has fueled a persistent fringe theory that the ancient Egyptians possessed some form of advanced electrical or optical technology, a literal light in the darkness, lost to time. The so-called light has become a staple of alternative history, presented as clear proof of impossible knowledge. The truth, however, lies not in forgotten engineering, but in understanding the rich symbolic language of Egyptian religion. Egyptologists universally interpret the scene as a profound religious metaphor. The bulbous shape is not a glass enclosure, but a depiction of a lotus flower, a sacred symbol of creation and rebirth emerging from the primordial waters. The snake within represents the sun god Ra traveling through the night in his bark, a journey of death and resurrection. The entire tableau is a visual hymn to the daily cycle of the sun, a cosmic event rendered in stone according to strict artistic conventions. The figure holding the object is not a technician, but a deity or a priest facilitating this divine passage. To interpret this as a technical diagram is to strip it of its cultural and spiritual meaning, to see a wiring schematic where the artist saw a prayer. The relief serves as a perfect and necessary cautionary tale for our entire exploration. It shows how easily a pattern-seeking human mind, conditioned by its own technological world, can project its own inventions onto the symbols of a different age. We see a light bulb because that is a dominant form of illumination in our lives. The ancient Egyptians saw the sun cradled in a lotus, promising a new dawn. This is the fundamental tension at the heart of any claim about anomalous technology. Are we uncovering a genuine thread of lost knowledge, or are we simply holding up a mirror to our own assumptions? The myth reminds us to proceed with humility, to first seek understanding within the artifact's own cultural context before leaping to revolutionary conclusions. It teaches us that the most compelling evidence is often not what we see at first glance, but what we learn when we listen to what the past is actually trying to say. This insistence on context is not a stubborn refusal to wonder, but the very bedrock of how archaeology builds a reliable picture of the past. For mainstream scholars, the case for widespread ancient precision optics collapses not under a single piece of evidence, but under the weight of profound, systematic silence. Their skepticism is rooted in a few fundamental principles of historical interpretation, rules of the detective game that prevent exciting stories from overriding the available facts. The first is a guiding light known as razor, the idea that the simplest explanation consistent with the evidence is usually the correct one. When faced with the Nimrud Lens, the simplest path is not to envision a lost Assyrian optical science. It is to see a polished cabochon, a decorative element whose slight magnifying power is an accidental byproduct of its shape. This principle asks us to exhaust all mundane possibilities before invoking extraordinary ones. The second, and perhaps most critical principle is the demand for corroborating evidence. A single, anomalous object is a mystery. A technological tradition, however, leaves a trail. If lenses were being deliberately crafted, even by a small guild of elite artisans, we would expect to find the echoes of that craft everywhere. We would expect to uncover the workshops with the specialized grinding tools, the half-finished rejects, on the artifacts themselves that match a lens grinding process rather than general lapidary work. We would expect to find them in a variety of contexts, not as rare, isolated curiosities. Most importantly, we would expect to find them mentioned, described, or even just casually referenced in the vast textual records these cultures left behind. The Assyrians recorded everything from grain shipments to astronomical omens. The Romans wrote technical manuals on architecture, aqueducts, and siege engines. The complete absence of any instruction on lens grinding, any inventory listing such tools, or any philosophical discussion of their use is a silence so deep it becomes evidence in itself. The final, and most seductive, pitfall is anachronism, the mistake of imposing our modern worldview onto the past. We live in a society built on lenses, from our glasses and cameras to our smartphones and satellites. When we see a piece of shaped crystal, our minds immediately jump to its optical function, because that is what such objects mean to us. But to an Assyrian jeweler, a polished rock crystal may have held ritual significance, or simply been valued for its clarity and beauty, a symbol of status rather than a tool for sight. Interpreting it as a lens because it looks like one to our eyes is to ignore the cultural framework that gave it meaning. For the archaeological mainstream, these missing pieces form an insurmountable wall. Where is the coherent tradition? Where is the evolution of the technology, from crude beginnings to refined instruments? The lens, while impressive, appears as a stunning one-off, a masterpiece that seemingly led nowhere. Without a supporting ecosystem of knowledge, tools, and documented need, these objects remain fascinating outliers, not proof of a rewritten history. They are the equivalent of finding a single, modern stainless steel screw in a medieval castle, a clear anomaly that suggests contamination or a later intrusion, not that the castle's builders had a secret metallurgy. The skeptical view, therefore, is not a dismissal of curiosity, but a disciplined commitment to the story the totality of the evidence actually tells. It asks us to admire the Nimrud Lens for what it most likely was, a beautiful artifact of Assyrian craft, and to marvel at the lens as a testament to Viking ingenuity, without needing to insert them into a narrative they do not fit. In this light, the true mystery may not be how they made these things, but why the brilliant, observable principle of the lens remained a curiosity for so many centuries, waiting for the perfect moment in history to ignite a revolution. The term itself carries a heavy load of expectation and controversy. It stands for out-of-place artifact, a label coined not by archaeologists, but by cryptozoologists and writers in the field of alternative history, and is, by definition, an object that appears too advanced for the time and culture from which it comes, or one that seems to challenge our established historical timelines. It is a classification born from a sense of anomaly, a feeling that something just does not fit. For many, the Nimrud Lens is a textbook, a piece of precision-shaped crystal sitting calmly in an Assyrian storeroom centuries before its time. Applying this label does something powerful. It immediately frames the object as a puzzle, a key to a hidden door. It invites us to question the official story and to consider possibilities that mainstream scholarship might overlook. In this sense, the concept serves a valuable purpose. It reminds us that history is not a closed book, that new discoveries can and should force us to re-examine our assumptions. It gives a name to that thrilling sense of cognitive dissonance we feel when the past presents us with something wonderfully inexplicable. But this same label comes with significant baggage, a set of associations that can poison the well of genuine inquiry. In popular culture, are rarely presented as neutral puzzles. They are often bundled together in lists of impossible relics, presented as definitive proof of lost civilizations, ancient astronauts, or deliberately suppressed knowledge. The lens from Nimrud might be discussed alongside claims of Egyptian light bulbs or thousand-year-old batteries, in a context where skepticism is framed as closed-mindedness. This sensationalist packaging creates a major problem for serious investigation. When an object is branded in the popular imagination, it becomes magnetized. It attracts extreme theories and often pushes away the very experts, the archaeologists, historians, and materials scientists who are best equipped to study it. Why would a university researcher risk their professional reputation by dedicating time to an artifact that the public already believes is evidence of Atlantis? The association with fringe theories can make the object academically radioactive, something to be cautiously noted in a museum catalog but not actively pursued with fresh grants or cutting-edge analysis. This creates a tragic feedback loop. The mainstream, wary of the sensationalism, gives the object a wide berth. This lack of new, rigorous study is then cited by alternative circles as proof of a cover-up or institutional stubbornness. The artifact becomes stuck, frozen between two narratives, one deemed too wild to be credible and the other too cautious to be exciting. The real casualty in this divide is the object's own story. The nuanced, often mundane truth gets lost in the noise. The label, in its quest to highlight a mystery, can actually prevent us from solving it. It encourages us to jump straight to the most extraordinary explanation without first exhausting the ordinary ones. It asks what if this is a lens, instead of first asking what else could this polished crystal be. By skipping those foundational questions, we may never discover the more fascinating, culturally specific reality. Perhaps the Nimrud object was part of a ceremonial standard, its clarity symbolizing divine sight. Maybe it was a unique burnishing tool for a specific type of metal leaf. These possibilities are not as headline-grabbing as ancient optics, but they connect the object to the lived world of the people who made it. They are answers rooted in context, not in contradiction. The baggage of the label, then, is that it can prematurely shut down the very process of open-ended, evidence-driven discovery it claims to champion. It trades the slow, careful work of archaeology for the instant gratification of a rewritten history. The next time you encounter an object labeled N, it is worth pausing to ask two separate questions. First, what makes this object seem out of place? And second, what cultural or practical purpose, now forgotten, could make it perfectly in place? The space between those two questions is where the most genuine historical mysteries and their most satisfying solutions are often found. So how do we move past speculation and into something more concrete? The debate shifts from dusty museum cases to modern laboratories and workshops, where a different kind of detective takes over. Experimental archaeologists and materials scientists approach these controversial objects not as symbols, but as puzzles of physics and craft. Their method is elegantly simple. They try to make them again. Using only the tools and materials available to the original culture, they attempt to replicate the artifact from scratch, documenting every step of the process. The goal is not to prove a theory, but to answer a practical question: what does it take to create this object, and what does that journey reveal about its intended purpose? This hands-on approach transforms abstract arguments about ancient optics into tangible experiments with stone, abrasives, and human skill. For an object like the lens, the replication process begins with a raw piece of rock crystal, a form of quartz harder than steel. The artisan, using period-appropriate bow-driven drills tipped with abrasive powders like emery or diamond dust, must slowly, painstakingly grind the crystal into a disc. Then comes the delicate work of shaping both faces into those specific, asymmetric curves. This is not a matter of random polishing. It requires a consistent, controlled motion to achieve a uniform curvature that will bend light predictably. Researchers who have undertaken this task report that it is immensely difficult, demanding hundreds of hours of focused labor. The very difficulty of the process becomes its own kind of evidence. If creating a lens-shaped object with intentional optical properties is this arduous with ancient methods, it strongly suggests the original was made for a deliberate, high-value purpose. No one spends weeks grinding a perfect crystal disc just to use it as a paperweight. The investment of time and rare material implies a significant function. Conversely, if a similar shape can be achieved quickly as a byproduct of creating, say, a decorative bead, then the optical property is likely incidental. These replication studies meticulously measure the outcomes. They test the focal length of the finished replica, its ability to magnify text, its efficiency as a burning glass. They compare these results to the original artifact. Often, the findings add nuance rather than delivering a final verdict. A replicated style lens might indeed function well as a magnifier, supporting the tool theory. But the process might also reveal that achieving a clear, undistorted image is nearly impossible with the technology of the time, pointing back toward a decorative or symbolic role. The experiment becomes a dialogue with the past, where each blister on the modern artisan's hand, each slight irregularity in the grind, whispers clues about the priorities and limitations of the original maker. It grounds our high-flying theories in the gritty, practical reality of how things were actually made. Rock crystal has always held a unique power in the human imagination. Long before anyone wrote a treatise on the physics of light, this perfectly clear, cold stone was seen as something extraordinary, a piece of the heavens or the eternal ice captured within the earth. Across countless cultures, from ancient Mesopotamia to medieval Europe, it was not shaped for what it could do to light, but for what it symbolized. Its flawless transparency represented purity, clarity of thought, and a direct connection to the divine. In a world filled with opaque materials, a substance through which you could see was inherently magical. This deep and well-documented symbolic role offers a compelling, mainstream alternative for many of the controversial crystal artifacts. Perhaps we have been asking the wrong question, looking for a workshop tool when the object was always intended as a spiritual key. Consider the Assyrian Empire that produced the Nimrud Lens. They were master craftsmen, yes, but they were also a society steeped in omens and rituals, where every aspect of life was connected to the will of the gods. Royal inscriptions and temple inventories describe objects made of precious stones for ceremonial use. A polished piece of rock crystal, especially one shaped into an elegant oval, would have been a prized possession. It could have been an inlay for a royal scepter, a symbol of the king's clear-sighted judgment. It might have been set into the eye socket of a cult statue, representing the deity's all-seeing gaze. In such contexts, its slight magnifying property is irrelevant, a mere physical curiosity. Its true value lay in its appearance, its rarity, and the skill required to work it. The crystal was not a lens to see the world more clearly. It was a token to help one be seen more favorably by the powers that ruled the world. This symbolic use only grew stronger in later periods. In medieval Europe, rock crystal was explicitly linked to the sacred. It was used to craft reliquaries, the ornate containers that held the physical remains of saints. The crystal panels allowed the faithful to glimpse the sacred contents within while protecting them, a perfect metaphor for the divine made partially visible. Bishops and abbots carried crystal-headed croziers, their clarity signifying the purity of the church. Nobles wore crystal amulets, believing the stone could ward off evil spirits or illness. In this worldview, the material was not chosen for its optical precision, but for its perceived incorruptibility and its ability to channel spiritual light. A Viking artisan on Gotland, embedded in trade routes that stretched to Constantinople, would have been acutely aware of this symbolic value. The beautifully polished disc, found in a grave, fits perfectly into this tradition. It may not have been a tool for a jeweler's bench, but a grave good of immense personal significance, a talisman intended to guide its owner with clarity into the afterlife or to signify their high status among the living. The argument here is not that these cultures were ignorant of crystal's physical properties. They almost certainly noticed that a rounded piece could sparkle in the sun or distort an image beneath it. But noticing a property is a world away from systematically engineering it for a practical purpose. The primary driver for investing dozens, perhaps hundreds, of hours into shaping this notoriously difficult material was far more likely to be spiritual prestige or social display than a desire to magnify text or solder a joint. When we examine a polished crystal artifact through a purely technological lens, we risk missing its true cultural resonance. We see a potential scientific instrument, while its maker may have seen a conduit for prayer, a badge of office, or a piece of frozen magic. This symbolic explanation is not a boring alternative to a thrilling mystery. It is often a deeper and more human story. It connects the object to the hopes, beliefs, and social structures of the people who cherished it, anchoring it firmly in the rich, documented tapestry of its time, rather than leaving it as a lonely anomaly adrift in history. This idea of a specialized, lost craft offers a compelling third path between mainstream skepticism and fringe speculation. Proponents of this view argue we should not expect to find a widespread optical science, but rather a tightly held workshop secret, a trick of the trade known only to a few master artisans serving royal or religious elites. In this scenario, the knowledge of how to shape a crystal to bend light was not a published theory, but a hands-on technique passed from master to apprentice over generations, a valuable proprietary skill as guarded as a secret recipe. Its purpose was intensely practical, not philosophical, to create a tool that enabled other luxuries, like engraving impossibly tiny seals or soldering the finest filigree. This craft would have existed in isolated, privileged pockets, perhaps in the workshops of Assyrian kings, Viking master smiths, or the ateliers serving Roman emperors. When that specific workshop tradition died out, perhaps due to political upheaval, the death of a master without an heir, or a shift in artistic fashion, the knowledge could have simply evaporated. It would not have been lost from a library because it was never written down. It would have vanished from the hands and the eyes, leaving behind only the exquisite objects that seemed to demand its use. This is not an unprecedented concept in history. We speak of lost technologies like Greek fire, the terrifying incendiary weapon of the Byzantine Empire. Its exact composition and delivery system were state secrets of such immense value that they died with the empire that guarded them. Similarly, the method for forging the legendary Damascus steel, with its distinctive watery pattern and legendary strength, was lost for centuries, its secret seemingly embedded in the specific ore and forging techniques of a particular time and place. These were not sciences in the modern sense. They were artisan technologies, dependent on specific materials, environmental conditions, and tacit knowledge that was never fully systematized. Could precision lens grinding have been the same, a brilliant but fragile thread in the tapestry of ancient craftsmanship? If so, it changes the nature of the mystery entirely. The question is no longer why a whole civilization failed to develop optics, but why a brilliant technical insight, born in the service of art and power, failed to jump the gap from the workshop to the world of ideas. It remained a tool, never becoming a telescope. It solved immediate problems of making and seeing beautiful things, but it did not spark a revolution in how humanity saw its place in the cosmos. The flame was lit, but it stayed in a lantern, never set to the kindling of broader scientific curiosity. This possibility carries a certain melancholy. It suggests our ancestors may have held pieces of the puzzle long before we assembled the full picture, their genius channeled into objects of beauty and status rather than instruments of discovery. The lost thread was not one of capability, but of application. A single brilliant tool does not rewrite history. For a technology to truly take root and transform a society, it needs more than just a clever inventor. It requires a fertile social ecosystem. Imagine a lone Viking artisan on Gotland polishing his crystal lens in a quiet workshop. He may have understood its power to magnify a rune or focus a flame, but if that knowledge lived and died with him, it remains a historical footnote, not a turning point. True technological revolutions are social phenomena. They require, first, a community of practitioners. This means not one genius, but many hands, many minds working on the same problem, sharing failures and breakthroughs. A guild of lens grinders, a network of opticians, a circle of natural philosophers exchanging letters. Second, they demand a reliable system for transmitting knowledge. This is how craft secrets evolve into reproducible science, through apprenticeships, written manuals, published diagrams, and public lectures. The formula cannot be locked in a single master's head, it must flow outward. Finally, and perhaps most crucially, there must be a persistent, widespread demand that drives iterative improvement. Why make a slightly better lens? Because 1,000 aging scholars are desperate to read, because astronomers are competing to map the heavens, because naval powers need sharper spyglasses to spot enemy sails. This demand creates a market, it funds research, and it rewards each incremental step forward. These three conditions, a community, a transmission system, and a driving demand, form the invisible scaffolding upon which technologies are built and sustained. Look at the uncontested rise of the reading stone and then eyeglasses in late medieval Europe. All three conditions were vividly present. Communities of glassmakers in Venice and spectacle makers in Germany honed the craft. Guilds regulated quality and trained apprentices, creating a clear transmission line for skills. And the demand was overwhelming, fueled by the spread of literacy, the rise of universities, and an aging population of clerics and merchants. This was a perfect storm of social factors, turning a neat trick with glass into a world-changing technology. Now, look back at the Nimrud Lens or even the artifact. Where is the community? We have no evidence of Assyrian lens grinding guilds or Viking optical workshops. Where is the knowledge transmission? No cuneiform tablets on focal length, no sagas praising the far seer's stone. And the demand, a hypothetical need for a jeweler is a niche application, not a societal imperative strong enough to push the technology from a rare curiosity into common use. This is the core reason these objects, however fascinating, did not spark a revolution. They were sparks that fell on damp tinder. They lacked the social oxygen, the sustained cultural breath needed to turn a flicker into a flame. The genius of the scientific revolution was not merely in building better telescopes, it was in creating the societies that wanted them, debated them, funded them, and taught the next generation how to make them even better. An isolated artifact is a whisper of what one person might have achieved. A technological revolution is the roar of an entire civilization learning to see in a new way. Accepting these artifacts as genuine lenses would do more than add an earlier chapter to the story of optics. It would subtly reshape our entire understanding of how science itself grows. The standard narrative we cherish is one of clear, linear ascent. It begins with the philosophical speculation of the ancient Greeks, passes through a long period of preservation and commentary in the Islamic world and medieval Europe, and then explodes into the experimental, instrument-driven revolution of the 16th and 17th centuries. This is the story of a torch being passed, a steady march from asking questions about nature to actively testing those questions with tools. It is a clean, satisfying arc of progress centered squarely on early modern Europe. But what if that arc is not the only story? The existence of precision optical tools centuries or even earlier would imply something deeply significant, that the crucial spark of instrument-based inquiry, the very heart of the scientific method, did not ignite once in a specific time and place. It would suggest that this spark could flicker into life in isolated pockets, nurtured by practical need and artisan genius, long before it caught and spread into a transformative fire. This is not about claiming the Vikings had a full-blown scientific revolution. It is about recognizing that the mindset which fuels such a revolution, the desire to extend human senses with crafted tools to see more clearly, might be a recurring human impulse, not a one-time invention. The implications ripple outward. If a master artisan in Assyria or on Viking Gotland was deliberately shaping crystal to control light, they were engaging in a form of empirical technology. They were not just thinking about the world, they were intervening in it with a crafted object, observing the results, and refining their technique based on those observations. This is the core of experimental science, albeit applied to a very specific, practical goal rather than to abstract natural philosophy. It means the seeds of an instrumental approach to knowledge, which we associate so strongly with figures like Galileo and his telescope, were potentially sown far earlier, in workshops rather than universities, by hands as much as by minds. This challenges the idea of a single, continuous line of progress. It suggests instead a history of science that is more like a patchwork, with brilliant threads of technical insight appearing, being used for a time, and then fading when the social conditions to sustain and expand them were not present. The narrative shifts from a straight line to a series of possibilities, some of which flourished into lasting traditions, while others remained as brilliant but fragile threads, waiting to be rediscovered and rewoven into a larger tapestry. This does not diminish the triumph of the scientific revolution, but it does complicate its origins. It asks us to see it not as a sudden dawn after a long night, but as a powerful convergence where many scattered threads, including perhaps these forgotten optical techniques, were finally drawn together by a culture uniquely prepared to weave them into a new and world-changing fabric of understanding. The debate ultimately circles back to a fundamental principle of scientific reasoning, one famously articulated by the astronomer Carl Sagan. He reminded us that extraordinary claims require extraordinary evidence. This is not a dismissal of wonder, but a call for intellectual rigor. It is the standard we must apply to the idea of ancient precision optics. The claim is indeed extraordinary. It suggests a sophisticated technological understanding appearing thousands of years outside its accepted timeline, in cultures that left no written record of such an achievement. So what kind of evidence would be strong enough to meet this high bar, to shift a fascinating anomaly into a settled historical fact? It would need to be evidence that leaves little room for alternative, more mundane explanations. For instance, imagine archaeologists uncovering a dedicated workshop site, not just a single polished crystal, but a collection of lens blanks in various stages of completion. These would be discs of rock crystal or glass, clearly shaped with the intention of becoming lenses, their forms too specific for jewelry or ornament. Alongside them, we would hope to find the specialized tools of the trade, perhaps grinding stones with concave grooves matching the intended lens curvature, or fine abrasive powders stored in containers, their grit analyzed and found to be purposefully graded for optical finishing. This would be a smoking gun, a clear snapshot of a craft in action. Even more compelling would be an unambiguous depiction in a contemporary technical manual. A detailed diagram in an Assyrian or Roman engineering text, showing the step-by-step process of grinding a lens, calculating its focal length, or even instructions for its use in magnification or fire starting. Such a document would anchor the technology firmly within the intellectual world of its creators, proving it was not a secret, but a shared and teachable knowledge. Without evidence of this caliber, the artifacts remain in a frustrating limbo. They are extraordinary objects, but they are not yet extraordinary evidence. They whisper a possibility, but they do not shout a proof. This high burden is not meant to stifle curiosity, but to protect the integrity of the historical record. It ensures that the stories we tell about the past are built on the firmest foundations we can find, so that when we do rewrite a chapter, we are doing it with confidence, not just with hope. The story of these ancient crystals is far from a closed book. In recent years, modern science has begun to re-examine these enigmatic objects with tools their creators could never have dreamed of, searching for answers not in speculation, but in microscopic detail. Advanced techniques like three-dimensional surface metrology, which maps an object's topography with incredible precision, are now being applied to artifacts like the lens. This process does not rely on the human eye to judge smoothness or intent. Instead, a laser scanner builds a digital model of the lens's surface, revealing every hill, valley, and tool mark at a scale of micrometers. Researchers can then analyze this model to determine if the curvature is consistent and symmetrical, the hallmark of intentional optical shaping, or irregular and random, suggesting a decorative polish. This kind of analysis moves the debate from what something looks like to what its physical form definitively reveals about the maker's process. Similarly, residue analysis using high-powered microscopes and spectroscopy can detect traces of ancient abrasives or polishing compounds embedded in the crystal's pores, potentially linking an object to a specific workshop technique. These are the quiet, meticulous methods of 21st-century archaeology, seeking to replace centuries of debate with quantifiable data. This renewed interest is not merely theoretical. There are ongoing academic projects dedicated to re-examining these optical anomalies. While no single, definitive study has yet rewritten the textbooks, small teams of archaeologists, historians of science, and materials engineers are collaborating to take a fresh look. Their goal is often to reconstruct the operational sequence, from raw quartz crystal to finished object. They ask new questions. Can the specific wear patterns on the lens tell us if it was held in a metal setting, suggesting a purpose-built tool, or if it shows signs of being mounted as a decorative element? Does the microscopic direction of polishing strokes indicate a technique optimized for creating a clear focal point, or simply for achieving a brilliant shine? These projects proceed slowly, without the fanfare of television documentaries, but they represent the most legitimate pathway for the controversy to ever reach a resolution. They acknowledge that the question, while burdened by fringe theories, is rooted in genuine physical objects that deserve the fullest scrutiny our era can provide. The potential of these new techniques extends beyond famous examples. Imagine a museum storage drawer containing hundreds of polished stone objects, cataloged simply as beads or decorative inlays. A systematic scan using portable surface metrology equipment could, in theory, identify any that possess a uniform, lens-like curvature hidden among them. Such a survey could reveal whether the lens was a spectacular one-off, or if it represents a broader, unrecognized class of artifacts. This is the promise of modern technology, not to prove a preconceived idea about ancient astronauts or lost civilizations, but to illuminate the true diversity and sophistication of ancient craftsmanship. It allows us to see these objects not as problems to be solved, but as conversations to be reopened, with new tools allowing us to listen more closely to the story etched in stone and light. The final verdict on ancient precision optics may still be pending, but the investigation, now armed with lasers and algorithms, is very much alive. This pattern of isolated brilliance is not unique to optics. History is dotted with technologies that seem to appear fully formed, like islands of advanced capability in a sea of simpler practice. Consider the mechanism once more. Its intricate bronze, modeling the erratic motions of planets, represents a pinnacle of mechanical engineering that would not be matched for over 1,000 years. Yet, we have no other devices like it from the ancient Greek world, no lineage of simpler astronomical clocks that led to its creation. It stands alone, a masterpiece of what we might call craft science, a deep understanding of materials and mathematics applied to a specific, high purpose, existing entirely outside of any formal scientific institution. The knowledge to build it was real and profound, but it remained locked within a small circle of artisans and patrons, never becoming a widespread field of study. The The same can be said for the miraculous durability of Roman concrete. Modern engineers are still unraveling its secrets, particularly how seawater actually strengthens it over time through the formation of rare crystalline structures. The Romans did not have a molecular theory of chemistry. They did not understand reactions in the terms a modern materials scientist would use. They arrived at this incredible recipe through centuries of practical experimentation, observation, and refinement at the worksite. It was a technology born from trial and error, from the hands of countless engineers and builders who passed down a winning formula without necessarily grasping the full scientific why behind its success. Their knowledge was empirical, embedded in practice rather than published in theory. This is the crucial parallel to our mystery of ancient optics. In both cases, we see a stunning technological outcome achieved through a deep but localized mastery of craft. The artisan grinding a lens to a precise asymmetric curve did not need to write a treatise on focal length and refractive indices. He needed to know, through practiced feel and inherited technique, that shaping the crystal this particular way made it better at starting a fire or magnifying a detail. His understanding was in his hands and his eyes, in the muscle memory of the grind and the visual test of the result. This craft science is a powerful, often overlooked, engine of innovation. It operates on a different track than the academic science that emerged later. It is not concerned with universal laws, but with specific solutions. It prioritizes repeatable results over explanatory models. And because it is so often tied to guild secrets, royal patronage, or isolated workshops, it can blaze brightly and then vanish, leaving behind only its most durable products as cryptic evidence of its passing. When we look at a polished crystal lens or a 2,000-year-old gear, we are not necessarily looking at proof of a lost civilization with our level of systemic knowledge. We are likely looking at the peak of a specialized craft tradition, a testament to what human ingenuity can achieve when focused on a singular problem, with all the brilliance and fragility that such a focused tradition entails. The weight of the evidence rests on a delicate scale. On one side, we have the physical objects themselves, tangible and undeniable. The lens, with its precise asymmetric curves, feels too intentional to be a mere bauble. The microscopic demands of the mechanisms, gears, and the impossibly fine lines on Roman intaglios present a powerful, indirect argument, a logical plea for some form of visual aid. These are not vague legends, but solid artifacts that seem to whisper of a practical, hands-on optical knowledge. They suggest a world where the extension of human sight was not a philosophical dream, but a workshop reality for a select few. This side of the scale appeals to our intuition, to the simple question of how such things could be made by eyes alone. It argues for a history rich with pockets of forgotten genius, where brilliant techniques were born, used, and lost within the closed circles of master artisans. The story here is one of human ingenuity flourishing in quiet, specialized corners, long before it marched onto the main stage of science. The other side of the scale holds the formidable weight of context, or rather, the profound lack of it. Archaeology builds its narratives not on single objects, but on patterns, on the echoes of a whole way of life. Where are the lens-grinding workshops, the toolkits, the half-finished rejects that mark a sustained craft? Where is the textual evidence, the single invoice, the passing mention in a letter or a manual? The silence from cultures that documented everything from tax records to temple rituals is overwhelming. Furthermore, the alternative explanations are robust and culturally grounded. The symbolic power of rock crystal as a sacred, pure material is well documented across, offering a compelling reason for its painstaking shaping that has nothing to do with optics. A polished crystal could be a seeing stone for the soul, not for the eye. This side argues that we must first understand an artifact through the world that created it, and in that world, the simplest explanation is often the most likely. It cautions us against the seductive trap of seeing our own technological reflection in every shiny, curved surface from the past. The current academic consensus leans heavily on this latter view. Most historians of science and archaeologists see these objects as fascinating outliers, brilliant examples of lapidary art or symbolic regalia, whose optical properties are incidental byproducts of the quest for beauty or spiritual meaning. They are not dismissed, but they are firmly placed within the known technological and cultural frameworks of their times. The consensus holds that the true, transformative journey of optics, from reading stone to telescope to microscope, is a uniquely traceable story, one that required the specific social conditions of late medieval and Renaissance Europe to ignite and sustain itself. In this view, the Nimrud and lenses are not precursors to that revolution, but parallel experiments that led nowhere, sparks that faded without kindling a broader fire. And yet, the mystery persists, and it persists for a good reason. Consensus is not the same as certainty. The nagging question of how certain feats of microengineering were achieved without visual aids may never be fully settled to everyone's satisfaction. The possibility remains that we have underestimated the tactile skill and visual acuity of ancient craftspeople, or that we have yet to recognize the true tools of their trade. The artifacts sit in their museum cases, silent and stubborn, refusing to be fully explained by either the mundane or the miraculous. They represent a gap in our understanding, a small, intriguing crack in the smooth narrative of progress. This crack may never be wide enough to rewrite the textbooks, but it is wide enough to let in a fascinating light, one that illuminates not a lost superscience, but the profound and often solitary heights that human craftsmanship could reach. The story they tell may not be one of ancient opticians, but of the breathtaking potential of the human hand and mind when focused on a singular, beautiful task. That in itself is a revelation worth seeing clearly. Ultimately, the crystal remains silent, holding its secrets close. The evidence for ancient precision optics, while deeply intriguing, remains controversial and inconclusive. These artifacts do not form a new timeline, but they do draw a fascinating boundary around our understanding. They exist as edge cases, anomalies that sit precisely at the limit of what our current historical models can comfortably explain. They challenge us not to rewrite history in a single stroke, but to refine the very tools we use to read it. They ask archaeologists, historians, and scientists to remain open to nuance and complexity, to listen for whispers in the data without ever abandoning the disciplined rigor that separates storytelling from scholarship. The true value of these objects may lie less in what they prove, and more in the questions they force us to ask about craft, knowledge, and the silent spaces in our records. The past has a stubborn habit of holding surprises that complicate our narratives of linear progress. It reminds us that human ingenuity does not always march in a straight line, but sometimes flickers in isolated brilliance, leaving behind puzzles that endure for centuries. If this exploration of forgotten light has sparked your curiosity, we would love to hear your perspective. What do you think these ancient crystals truly represent? Share your thoughts in the comments below, and as always, thank you for joining this journey into the shadows of history.